Can your doctor cure your sickness without identifying the problem? Can your professor or project manager make the project work in a smooth manner without identifying what is going wrong with the project? Yes, this is particularly the idea of today's video. Topology, as we know, is full of counterintuitive ideas, seemingly paradoxical problems, and a lot of mind-bending curves and twists which keeps us struggling and which keeps our mind always in a very confused state. But without identifying the problem, without identifying where we are going wrong or why we are facing those problems in topology, we won't be able to identify and find out a proper solution. In today's video, I would be talking about what are the problems, what are the difficulties, or what are the hindrances that you face while you are studying topology as a subject, and what are the indigenous solutions that we can find out, or rather the mathematicians have find out, so that the learning and the understanding of the topology is much more easier. So today's video, remember, is basically identifying the problems, identifying the pain that you face while understanding and learning topology, and what could be the best and the easiest solution in order to overcome this type of problem. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this new video on topology, Untangling Topology. Let me be very honest with you. The objective of today's video is not to teach you topology. The objective of today's video is basically how, when you are learning the subject of topology in your college or university courses, you can very well identify what are the problems. Once you identify the problems, you can definitely find out a solution, or you can seek a solution. Remember one thing, that throughout this journey we will not only identify the problems, but we will also tell you what is much more easier, and it is full of fun. Now, to unravel the topological notions that defy the common sense, we encounter a lot of things across topology. Continuity, homeomorphism, diffeomorphism. There are many concepts which you might find which is similar to differential geometry. Yes, differential geometry and topology, in some sense they're equal to each other, although there is a huge difference, because differential geometry deals with local manifolds and surfaces and topology deals on a global scale. However, the objective of this video would be to help you identify the problems, and these problems are not always mathematical problems. These problems can be something which are very mental, and there is a mental blockage, and there is a problem in terms of visualization, and most importantly, the problems in identifying and solving abstract problems. What are the abstractness that we face in topology, so that our reading is hindered, our problems are being doubled, and what we are facing coming up, which comes, is abstract concepts. And I agree wholeheartedly with you that abstract concepts are a problem in understanding any mathematical or subject in physics. Now, have you ever wondered that is it topology only that deals with abstractness? No. If I say you this one, for example, a squared, a to the power 2, or any kind of an exponential, or even if I say what is hypotenuse squared, don't you think this is an abstract problem? Don't you think that this is an abstract concept? Because if you go into the market, if you go into daily life, you go to colleges, markets, schools, bus, airport, anywhere, you won't find anything which is really a squared. You really won't find anything which is hypotenuse squared. You won't find anything which is a logarithm or an exponential. So what I am trying to tell is that please get out of this notion that only topology is full of abstractness. No, topology is one of the subjects that deals with abstractness. But if you start basic with linear algebra, even high school algebra, these are all concepts which are. So in order to deal with abstract concept, first I would like to show on your screen three basic concepts which comes along, which is called open set, neighborhood, and a boundary. Now, in order to understand open set, what I really request you to have a look on the screen. Now, an open set in topology can be considered as a collection of points. You see, this is kind of a room, and each point has a little room around that, and it is still a part of the set. You can think of as a cafe, where an open set could be a collection of chairs, and each chair has enough space around you to sit comfortably and enjoy the cup of coffee with your friend. So first of all, whenever you're facing this type of an abstract concept, rule number one is to draw a picture. You go to any professor, mathematician, they will say, no, this is not the right teacher, this is not the right concept, but you have to come into something like this, and they will ask you to write those sets, unions, intersection. But I would request, when you're dealing with abstract concept, the first thing that you need to do is that draw an analogy. Draw anything which is very comfortable with you. For example, a coffee shop where you have got a lot of chairs, and these chairs are connected to each other, and these chairs, because they're connected, there is enough room, and you can call it as an open set. Second thing I would like to show right on your screen is that a pond, for example, which has got no islands, can be considered as an open set. Why? Because any point in the pond can be surrounded by a smaller open set. For example, if we take this pond, and right in the middle of the pond we can surround it by a smaller pond, then it is completely contained within the larger pond. So you take a pond and you surround it with another pond, and what happens is that the smaller pond is completely contained within the larger pond. So if we take, say, for example, pond as an island, then we want to show that it is an open set. We can do this by showing that any point in the pond can be surrounded by a smaller and open set. Isn't it wonderful? You can compare with coffee shop, pond, or whatever you like, but this is a kind of an abstractness that students first face when you're learning open set. The second thing which comes across is what is a boundary. Now, these things I will surely explain in this part of our video, that why we are dealing with open sets and boundary, and why we are not content to metric spaces. So boundary is something you can see when it starts like you are stepping outside the cafe. You might not be inside that open set, that is inside the cafe, but still you are close enough to get a sense of the ambience. That means you're just stepping outside, although you're not in the open set, but you can still enjoy the ambience of the cafe. This is something which you can think, although in an abstract way, to a solid understanding what is a boundary. Neighborhood, as you can wander around the cafe and always find a table with its own little space, you can think each point of this as a neighborhood. So each point's neighborhood includes other nearby points that are a part of same point. So neighbors, I mean to say, we have neighbors, you all have neighbors. Connection, so you can think of that it is a cafe set, and you can still engage into a kind of a cozy environment. Similarly, no matter which point you pick up in an open set, it is always connected to another point and preserves the set of characteristics. So obviously, I say I have a connection with you. That means that you are into the cafe's open set. I mean to say, you sit inside the cafe's open set and you can enjoy the cozy environment. Now, I cannot give you more example because there are a lot of examples in topology which deals with abstractness. So this is just a simple example that when you start learning topology, obviously come with a closed set, open set. Closed set is rather easy. Open set, neighborhoods, points, all those things. So try to get a kind of a hypothetical understanding, a coffee shop or a small pond, and try to connect those things with the learning. I know this won't be a rigorous understanding, but still I would say neighbors, these are not very familiar concept. These are not very common names, because neighbor means what? A neighbor. Connection means I have a connection with you, or internet connection, or laptop has lost its connection, something like that. Now these are known as topological notions, topological concept, which is very, very counterintuitive. What are those topological notions or topological concepts that we are really worried about? Coming up into the next part. First, let me show you what are the topological notions, or you can say terminologies, which are used in topology. So you see, we dealt with open set, then we have boundary, topological equivalence, continuous deformation, quotient spaces, non-Euclidean surfaces, and homotopy. Now what I want to make sure is that don't get confused or don't get puzzled that, oh my goodness, these things, how they are coming, we really don't know. I understand you really don't know, and there is a problem in terms of understanding. But as I told you, that when you go to a doctor, until the doctor identifies that whether you have a sickness or you have a diarrhea or whether you have a fever, it would be difficult for any doctor to identify. So try to understand that these are the new things that you are learning. These are new notions, and it will take time slowly to assimilate in your brain. First, I would like to show a very similar concept which you have dealt in calculus or otherwise. It is called the concept of continuity. Right on your screen. So you see the concept of continuity has changed. It is called a function is continuous if it preserves the topological properties of the spaces that it maps between. This is a subtle concept that can be difficult and sometimes need to be understood intuitively. So continuity, the basic essence is the same, but here it says that it preserves the topological properties, spaces that it maps between. So here is a map and here is a map. It is only continuous when things are, I would say, it preserves the topological properties. Whatever, the properties can be anything. I am smiling, you are smiling. Say for example, it can be a topological property, and that is being linked by something which is called a continuity. I have long hairs, you have short hairs. No, it is not preserving the properties, so it is not continuous. I mean to say these are very foolish examples, but anyway, so the continuity examples, you see this has changed, so it is a new notion. Next on your screen, the concept of homotopy. Two topological spaces are homotopic if they are continuously deformed into each other. This is a powerful concept that needs to be understood in topological spaces. So you see, these things you have not really learned in Euclidean geometry or school level or high school level geometry. So particular, I would say, thing, for example, if I consider this one, is a tomato ketchup, right? So somehow this particular shape will get deformed into some other shape. This particular shape, it is getting into deformed into other shape. So what it is telling that these two topological spaces, so if this one and maybe another thing which are into two topological spaces, they can be continuously deformed into each other. That is what is called a homotopy. For example, on your screen, the circle and the sphere are homotopic. This is because they can be continuously deformed into each other by stretching and bending. That's it. So homotopy, the best thing that you do, if you go back to my old one video where I have actually discussed using clay structure, then you can bend and stretch. So how these structures are getting deformed. This is another topological concept, notion. You understand that this is something which is absolutely not common in your use, the way you learn. So that is another notion. So all these things, for example, homotopy, for example, continuity, then there is topological spaces, then there are neighborhoods, a lot of other things in topology. There are jordancurvetheorem theorem and many other things. So try to understand that these are topological notions, these are topological concepts. Identify that what is going wrong. Are you not being understand homotopy? Use simple examples. So now right on your screen, what I would like to show you is that these 3 points. Use analogies. You can use any idiotic analogy. It doesn't matter. You don't have to tell anything to your professors or teachers. Use examples and use proofs. I mean to say, this is not the right one, that this particular shape can be deformed into other. However, a sphere can be deformed into a circle without stretching and bending. Take a ball, take a mud ball which can be stretched into a circle. Try to do that on hand. I don't have the equipments right now, otherwise I would have shown you. So use practical examples, take forms, clays and structures and make them and see whether the sphere is actually getting a homotopy or a transformation into circle. If it is, then it is called homotopy, and without tearing and gluing, if the topological properties, whatever the topological property is there, is it being preserved? Yes, it is preserved, then the function is continuous. So all these things which I am trying to tell, these are abstract things. These are topological concepts that you need to have. Now, most important is that all these concepts, continuity, for example, homotopy, homeomorphism, isomorphism, which are still there, these are all counterintuitive examples. That means these are not what we usually see or usually study in our early school days or in our daily life. These are called counterintuitive examples. There are a lot of counterintuitive examples, and the problem again identifying that what is counterintuitive and finding out a solution. Coming up in the next part of our video, how will you identify the counterintuitive examples and how will you understand? Please stay tuned. Coming up into the next. Counterintuitive examples are something which is not within our natural intuition, and when these things comes into our mathematics, we are puzzled, we are perplexed, and we feel frustrated that this is not the thing. But understand, now the thing is that if I talk that why these concepts came into, I mean to say why we are not talking of the Euclidean or general space or general manifolds, the reason is that there is a long history. Why topology evolved, what is the need for generalization, and you can go back to my video in topology. I think 2 years back I made an initial video, but it's called Topology and Topological Space, which actually tells you a little bit of history and the motivation what we have done. Coming back to the present, right on your screen you will see two very familiar figures. One is a Mobius strip and the second was a Klein bottle. Now right on your screen you see the Mobius strip is actually a surface with only one side and one boundary. This is obviously a counterintuitive example because it seems like Mobius strip should have two sides, but it does not. This is counterintuitive. So the problem is that do not fear that this is something counterintuitive. This is actually what Mobius strip is all about. It seems that it should have two sides, but it has one side. Now there is a lot of mathematics obviously involved in Mobius strip, but what I would request you is that make a Mobius strip. Construct a Mobius strip with a thin sheet of paper. Go to YouTube, there are a lot of videos on how to make a Mobius strip. The reason is that, as I told you, that we will identify and find out a solution. Until and unless you make a Mobius strip, you would never understand that why it shows like two sides yet it have one side. The second counterintuitive example, the Klein bottle, Felix Klein has discovered. It is a surface with no inside and outside. This is a counterintuitive because it seems like Klein bottle should have an inside and outside. Again, I know it is difficult to construct a Klein bottle, but however you can give a try. Go to YouTube and find out what is the way in which we can make a Klein bottle. So again, it is a counterintuitive example, obviously. Now we have identified what is a counterintuitive example and what is the solution. Make those these type of surfaces on your own hand, and then you will identify example, which is my favorite right now on your screen, is called a Jordancurve theorem and a Peano curve. Now what is Jordancurve? Let me show you in a quick example. So you see, a Jordancurve theorem states that any simply closed curve in the plane divides the plane into two regions, interior and exterior. The interior is the enclosed region. Take this kind of thing and draw a kind of a circle, then you will see that the circle divides the paper into. Now we have all drawn circles, but we have never noticed it. So it divides it into two sides. One is the region inside the circle and the region outside the circle. This is Jordancurve theorem. It's kind of a counterintuitive but very interesting. Right on your screen you see peanocurve theorem. It is a space filling curve, which means that it passes through every point in a given region. So peanocurve can be constructed, you can see right on the screen that it can be started at one corner of the square and then tracing by a continuous path that passes through every point of the square. So there is a 1, there is a 2, there is a 3, there is a 4, 5, 6 and so on. So this is also a kind of a counterintuitive example, but actually the solution is that you can draw that manually. You can make a piano curve by not lifting the pen. Just to summarize, what are those? Right on your screen, you see that the Jordancurve theorem, what it states, that any simply closed curve in the plane divides the plane into two disjoint regions, interior and exterior. The interior is the enclosed and exterior is the region not enclosed by the curve. So one is enclosed, one is not enclosed. Peano curve is continuous curve that fills the whole plane. This is counterintuitive. It fills it up and it divides it. This is counterintuitive. Why? Because it seems like a curve should only be able to occupy a finite amount of states. So any kind of a curve, it is. So you see that Jordan curve and Peano curve, although not Jordan curve, typically Peano curve is something which is very counterintuitive. The reason is that because it seems like a curve should be able to occupy a finite space, but it keeps on filling and growing. Now what I was trying to tell you right at the beginning of this video is that once we identify and we know that okay, these are counterintuitive phenomena, these are counterintuitive problems, and this is something which is not usually encountered, then we are mentally prepared and then we can find out the solution. So now at this phase of the video where we have been talking basically about topological notions, we talked about abstract concepts which we try to familiarize with certain analogies like a coffee shop or a small pond. We also have seen what are the counterintuitive examples, for example Mobius strip, Klein bottle, and topology is full of counterintuitive examples. How many will I make it in one video? You tell me. So you need to identify, you need to mentally understand that okay, this could be the problem, this could be something which we are going to encounter, and just find out through different resources. Even you can email me if you're finding a very difficult concept to conceptualize. I can help you out that what is the way mentally you can accept and mentally you can understand and then go into the deep mathematics. But even if I talk about all those things, what actually keeps the students busy is what is called how will I write a proof? How will I make a rigorous proof? And entire topology is driven on proof-based system. How do you do that? Coming up into the next part. You see, when you are doing with a proof-based mathematical system, for example, right on your screen, there are a lot of proofs which are there. The Jordan curve, the Brouwer theorem, the Borsuk-Ulam theorem, and topology is filled of proofs. Now, I already have made a video in how to write a mathematical proof. I am giving that link in the description box. I would request those who are watching this video finding it difficult to do proofs, I would request sincerely, please go and watch that video, because in this video if I start talking about how to make proofs, what are the steps, what are the things that you need to do, unnecessarily people watching for topology would lose interest, and also it would be too long of a video. But there are certain steps 1, 2, 3, 4 which you can do, and you should not skip those steps. You should write it in plain English. All of this I have actually discussed how to write a mathematical proof. The link is given in the description. Go ahead and check it. It would be very useful, and you can even start with simple proofs and then step-by-step guide into that, and I can assure you topological proof will be very easy for you. You need to check out that video and you can find out how to write proofs, and then you can come back to the notions of topology. The next concept which we face is what we call the notion of compactness. Now you see, what happens typically is that the notion of compactness actually is not speaking of lines, distances, points, but something which we call is being small enough, being close, being compact. Right on your screen there is a definition. The notion of compactness topology, why it is difficult to understand, because it introduces a non-intuitive concept of being small enough without a clear counterpart in a traditional geometry. Compactness is a fundamental property of topological property that captures the idea of space not escaping to infinity but being self-contained or well-contained. So you see, if you read again, as I told you, the history of topology, which I have told you to go and watch my video, then you will understand why human beings, why mathematicians have developed. The reason why we develop compactness is because the metric spaces needs to be generalized and generalized and generalized into much more broader field, and when this generalization happens, those distances, points and lines and the functions, they vanishes. So understand that now it is the time in topology. What is the problem? Problem is that there is nothing called a line or a distance. It is called nearness. It is called compactness. Why we are doing? Because we want to generalize the general notion of geometry to a much wider audience, much wider, I would say, application. Right on your screen you see compactness is abstract concept because compactness is a topological property that does not depend on the metric of the space. This is what I was just talking, that remember, we are not in a position, we are not in a world where we are defining metric spaces. Metric spaces do not exist. Again, you read that compactness is a property of the topological structure. It is not related to the way that the points in the space are spaced. This can make difficult visualization, etc. Now you need to understand. Now again, the solution is that yes, I understand that we are not into metrics. They are no longer lines. They are no longer distances. We cannot use Pythagoras or any theorem to calculate the distance. So why do we do? How much near the points are, how much compact the space is, how much close they are, and that is why we use closeness, compactness, and that is why neighborhood, all those things come into. So that is why it is not related to the way that points in the space are actually spaced, and it does not use any element of metric. See, basically the things happen is that mentally the biggest problem comes when we are moving out of the general notion that is no metric spaces, no distances, no Euclidean geometry. It is all about closeness. So here right on your screen you see there are many different ways to define compactness, and each definition has its own advantage and disadvantage. While the intuitive idea of being small aligns with compactness, its formal definition using open covers initially seems abstract and disconnected from the intuitive notion. So here are some of the quick solutions that you can do. Number one, start with using simple examples. I told you that this is how the lines are. There is no metric spaces, there is no line. Use diagrams. Yes, you can use diagram instead of line, making the same as a line. You make them that they are very close to each other. They are compact with each other. You read multiple sources because sometimes you might find that one source is not good enough. Please do read multiple sources, videos, books, lecture notes, etc. Visualize open curves. What are those curves are all about? And connectedness and compactness. Again, this is not the right time that I should explain, but connectedness and compactness again are closely related feature, just like homotopy and homeomorphism are very much closely related to each other. They are very close. Homotopy deals with something which is related to maps, mapping one function to other, whereas homeomorphism deals with something which is called topological space. So try to go through different kinds of example, try to understand the different kinds of sources, consult with your teacher, use diagrams, write certain things, draw certain things, but this is how the concept of compactness, or I would say again a counterintuitive understanding, will come into play. So the notion of compactness, just to summarize in a few words, is because we don't need metric spaces, we don't need lines, we are in a much more generalized geometrical platform where these things are close, these things are compact, and definitely there is a mathematical advantage. The biggest thing which comes that all this compactness, continuity and other things are related to some basic idea. I would say one basic idea which is called topological space. Why it is abstract? How do we understand? What are the methods in making understanding of topological space much easier coming into the next? Well, I have already made a video on topology and topological space. I have been citing the name of that video right from the beginning. You can go ahead. But try to understand that why topological space is again a difficulty and what do we need to do in order to understand. Right on your screen you see it introduces a new way of defining the concept of nearness and openness that might not align with our familiar Euclidean geometry. So topological space provides a more abstract framework for studying properties that remain invariant under continuous deformation. You see again a counterintuitive understanding, something totally different. We used to draw lines, we used to measure things, but now we are deforming things, we are twisting things, we are bending things. So if we twist that, if we bend that, say for example this one, if I bend that, sorry I won't be able to do that. If I bend that, If it gets bent, then what would be the next shape that it would be formed, and will that shape still preserve the concept of a Maggi tomato ketchup? Will it still have the spices? Will it still have the property? Will it still have that taste which is there in it? That is what is called the preservation of the properties of a topological space. If it does, A, B, C, D, these things will be done. If it does not, then it cannot be considered as a topological space. So if this particular shape needs to be deformed and it carries the same property, that is a taste and flavor and color and everything, then that can be called as something which is transferred to other and remains invariant. That is one of the concepts of topological space. Few important points right on your screen. It is a departure from metric spaces. It is an open sets and topology. And topology uses a lot of unfamiliar terminology, for example topological space, and that is why topological proofs in topological spaces can become complicated. So what could be the usual way in learning topological space? I will just quickly glance through the points already you know. One is that you need to review what is called a metric space, because here we are not dealing with metric space, but still you have to review metric spaces. It's important. Second would be that you need to basically have the definitions correct, because definitions are rooted. Many videos have told that you need to review the definition. Visualizations, again, it's a very important factor. If you are unable to visualize certain things, you won't be able to do. Non-metric examples from metric spaces, how you can move into non-metric examples. Learn that. Topological transformations, explore how functions between topological spaces can be continuous without direct reference direction. I just told you that something which will remain invariant, and used some real world analogy. Consider real world applications where topological spaces can be applied from here to here. This is a line, this is no more a line, this is a neighborhood, how close it is, how compact it is, that's it. This is again a kind of a guidance that how you are identifying the problem and how you are finding a solution of the problem. The basic thing which remains again is what we call is this one, non-metric approaches. Because our brain or our general thinking is wired to metrical approaches, lines and distance, that is why it becomes a kind of an issue. So non-metric approach is definitely one thing, but have you ever imagined that we are talking of these things, problems, identifying the problems, but what it lacks is that we cannot see topology around, and we cannot find there is any application of topology right now in front of us. Lack of application again leads to problems. What are those problems and how do you tackle coming up of applications? Well, I have to agree that research or certain abstract concepts, not only topology, group theory, ring theory, if you further read, all of these lack applications. But it is really not so. I mean to say, whenever a topologist or a mathematician is working on a particular concept, is it that it is just for the level of science? I was just talking to Professor Shantanu Chaudhary in the last, yesterday only, and I was telling that, sir, whatever the research you're doing, because he will be coming live in my channel, on 24th of September, he told that, Shaunak, we are doing science not for ours, but for the benefit of human mind, benefit of human beings. So the lack of applications in topology that you see right now, it won't remain, because topology is widely used in even aerospace and in space explorations. So yes, it lacks application, but try to understand why it lacks application, because the technology is not up to the mark that it would include those abstract concepts of topology and find something like a cell phone, like a car, or maybe a bike which will help us into our daily life. But it would definitely come up. Try to identify, yes, there are lack of applications, but it won't remain for long because it will come into use. Now we come to the central part of the problem in identifying all those issues and ideas, that is the mathematics, the level of mathematics that we know. What would be the good foundation of mathematics in order to learn topology, coming up into the next part of our video. Good foundation of mathematics, I won't be detailing you exactly A, B, C, D, what are the mathematics that you need to know, because you can go to my video, How to Learn Topology. book suggestions and the basic mathematics. Everything is given. That is a detailed video. But what I would like to tell you is one point. Remember that mathematics, not only for topology, especially when we are talking about topology, it is a cumulative knowledge. That means you build one upon one upon one upon one and slowly you go up. That means that understanding topology would require mathematics on a step-by-step basis. Mathematics would be required where you accumulate knowledge. Also try to understand that there is new way of thinking. Right on your screen, on the screen I would like to show you. Topology introduces a new way of thinking, emphasizing relationships and structures rather than numerical computations. This is a golden word. I would say this is very important. It is actually relying on relationships between spaces, between points, between neighborhoods, between topological spaces, and it does not depend upon numerical methods. And because our brain is wired to numerical methods, and that is the reason we find topology different, and that is why I'm making that video. So understand that the way of thinking in topology is totally different. You have to move out from the usual concept of metric spaces, distances, lines and curves, because what you think that the curve will take one place, you see it is infinite. What you think to be one-sided, two-sided, you find it to be one-sided. That means what we are doing is that we are not relying basically on computation. Rather, we are trying to find relationships. Just like human beings, it is not about just talking and giving deliveries over videos or any kind of a corporate relationship. It is finally we boil down that do you have a good relationship with that person? That means relationship mathematically as well as human beings, it is all that matters. How do you understand moving out from the concept of numerical analysis or numerical thinking into relationship building? Very important. Quick points. You need to start with the fundamentals. I have underlined that in red because that is very important. We often skip fundamentals. We keep on skipping fundamentals. Second is that take a good course, foundation course in mathematics. But I have forgot to mention over here also, you need to have a rigorous understanding of a proof-based mathematical system. Study set theory, logics and proofs, and even you can start with the real analysis. That would be good. Topology basics, that is again a very important part. You have to undergo what is called a topology basic. You can go back to my videos. There are certain videos which deals with topology basics. Solve problems, work through problems, and finally the last one which I have underlined is called patience and persistence. Yes, all my dear sons and brothers and sisters who are watching this video, topology is something even a genius like Terence Tao has told, it will take time. You have to be patient. You will fail one by one. Just I made a video. What are the things that you should avoid while doing physics? That is, you should not fear about failure. So first of all, what I would like to tell is that get the basics right, understand the basics of topology, and also have a complete fresher course on what is called a proof-based mathematical system. And this is not only true to topology, it is also true for differential geometry. Any kind of advanced proof-based mathematical system, I would go back to how to write a proof-based mathematical system. It gives you the steps, etc. Now there is one thing which is still pending, which I have not covered in the video, which is called a kind of a similarity between two close ideas. They are quite similar but seems to be different. What is that coming into this? So you see, this is something which is called continuity and homeomorphism. Now again, right at the screen you see continuity and homeomorphism sometimes can be difficult. Why? Because it is a departure from the intuitive geometric notions. These concepts involve understanding how points and sets in space relate to each other without relying on distances of traditional geometry. So again, this is the same concept which is coming, that we are not depending on the usual notion of geometry, but we are depending on something which is called relationships. Relationship between points, between sets, between manifold, between spaces, between neighbors. So understand that continuity and homeomorphism sometimes comes as a challenge, and what is the solution? Right on your screen. Continuity and homeomorphism are important. Continuity is a property of function. That means that the function does not tear or split the space which is defined. And homeomorphism is a stronger property of function, which means that it preserves the topological structures of the space as it is defined. So continuity is something which is a kind of a property that the function is not split up, it is not teared up. And homeomorphism is something which I define with this. That means if this particular shape is being deformed or changed into some other shape, will it carry the same color? Will it carry the same taste? Will it still feel like a sauce, or it will feel like a donut? So it preserves the topological structures and the space it is defined. So homeomorphism is basically related to the properties when it is deformed into other, whether it is maintaining that. Continuity is something whether the function is torn up, whether the function gets teared up or split up, something. But sometimes it comes as a very big confusion. Are they the same or something like that? Okay, so these are some of the quick solution. Study homeomorphism examples, like you can map a circle or an ellipse. Most importantly, visualize transformations. Now, for example, I can take any other transformation. For example, I take the box of my spectacle, right? Now, imagine that this particular spectacle is getting deformed into a circle. Imagine, try to find out. And there is something written on this box, right? So if it deforms into a circle, will it maintain that line? Will it maintain the shape? Will it maintain the same kind of a structure that is written? That is called the visualization of transformation. And if you continuously visualize, it really helps. The next thing, which is a little bit different, which is called a contrapositive logic. Understand the contrapositive of continuity. It is a function. If a function is not continuous, there must be counter example when an open set does not map to an open set. So if it is not continuous, if it has broken down, if it is not continuous, that means one set is not mapped into an open set. Try to draw that, try to write that. What is that contrapositive logic? That if it is not deformed, what it would do. If it is not preserving the topological space, what it would do. Analogies related to the real world analogies, like stretching or bending a shape or a rubber, which I just told. So you see, what happens basically is that the abstract concepts now are no more abstract concept, and this continuity, homeomorphism, Klein bottle, Mobius strip, n number of concepts. You only when you identify the problem which you are facing, you will yourself come out with it. So that's all for today's video, untangling topology. I think I have been able to untangle a lot of difficult concepts. So just to summarize in a few words, what we learned is that we need to identify the problem. Most of the time we do not identify the problem, and what we do is that we keep on doing the mathematics over and over, totally close like a bullseye, and we do not see around what is the problem. So the abstract concepts, you can use analogies in order to, I showed you the pond and the cafe example. There are different kind of topological notions which you can use analogies, examples and proofs. There are a lot of counterintuitive examples. Try to draw, make shapes out of clay or a paper or something, so that the counterintuitive problems become an intuitive understanding for you. And remember one thing, that all these things are being made in order to make life easier. It is not that topology is a curse or topology is something which will make life as a hell. No, it is something which will make things much more easier. We do not understand, as I told you, we are wired to metric spaces, we are wired to something which is called a distance or something like that. Also, another important concept in this video which we learned is that we are not dealing with computational problems, we are dealing with relationships, we are dealing with nearness, we are dealing with compactness. So once you identify those things, then you will come up with the solutions. I have already showed you what could be the kind of a solutions that you have, and I think if you can work on those solutions, topology would be very adventurous and a great learning. Thank you for watching this video. Please do let me know how did you like that video, and do you think that these are the methods, or if you have any other method, do let me know in the comment box. Please don't forget to hit the subscribe button, to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. I will be back. Lot of speakers are coming in the month of September. Lot of events happening. So stay tuned on my channel and thank you very much for watching this video.